Theorem 10.2, Equality of tangents from an external point. Welcome, everyone. Today, we are going to dive into a very important topic in circle geometry. In this subsection, we will examine one of the most fundamental properties of tangents to a circle. As we move through this lesson, you'll see that when we draw tangents from a point located outside the circle, a specific geometric symmetry emerges regarding their lengths. This symmetry is the key to understanding the theorem we are about to prove, so let's pay close attention to how these lines relate to one another. Theorem statement. The formal theorem states that the lengths of tangents drawn from an external point to a circle are equal. Now, that might sound a bit technical, so let me break it down into simpler terms for you. Imagine you pick any point, let's call it point P, located anywhere outside a circle. If you draw two straight lines starting from that point P that just graze the edge of the circle, touching it at points Q and R, the distance from P to Q will be exactly the same as the distance from P to R. Now that we have introduced the topic, let's look at the actual statement of Theorem 10.2. Essentially, the two arms or paths stretching from that single external point to the circle are perfectly identical in length. We are going to prove why this symmetry exists in the next few slides using both triangle congruence and the Pythagoras theorem. Detailed proof. In the next few slides, we are going to explore two different mathematical approaches. First, using the congruence of triangles, and second, using the Pythagoras theorem. Now that we understand the statement of the theorem, that the two tangent segments are equal in length, you might be wondering, how do we actually prove this is always true? Well, to give you a complete understanding, we aren't just going to rely on one method. This dual approach will help you see how different areas of geometry connect to reach the same logical conclusion. Setup and construction. First, let's imagine a circle with its center at point O now. Let's pick a point, which we'll call P, located anywhere outside the circle. From this external point P, we are going to draw two lines that just graze the edge of the circle. These are our two tangents. We'll label the two specific points where these lines touch the circle as point Q and point R. To make sense of the relationships between these points, and to prepare for the proofs we'll see in the next few slides, we need to perform a few simple constructions. First, let's draw a straight line connecting the center O to the first point of contact, Q. Next, let's do the same by joining the center O to the second point of contact, R. Finally, let's draw a line connecting the center O directly to our external point P. Now that we have established the theorem statement in the previous slide, let's move on to slide 4, where we will set up our geometric diagram. To prove this theorem, we first need to create a clear visual framework. By doing this, we've transformed a simple set of lines into a series of connected triangles, which will allow us to use triangle congruence and the Pythagoras theorem to complete our proof. Method 1, using triangle congruence, RHS Criterion. First, let's look at step 1, where we identify the right angles. There is a fundamental property of circles you must remember. A radius is always perpendicular to the tangent at the exact point where they touch. Because of this, we know that angle OQP is equal to 90 degrees, and angle ORP is also 90 degrees. This is crucial because it tells us that triangle OQP and triangle ORP are both right-angled triangles. Moving on to step 2, let's compare the sides of these two triangles to see how they relate. We can see two clear connections here. First, side OQ is equal to side OR because both are radii of the same circle. Second, notice that side OP is shared by both triangles. It is a common side, and specifically, it acts as the hypotenuse for both triangles. This brings us to step 3, where we apply the congruence rule. We now have all the necessary pieces. We have a right angle, we have equal hypotenuses, and we have one equal side. Therefore, we can conclude that triangle OQP is congruent to triangle ORP using the RHS, or right angle hypotenuse side, congruence criterion. Finally, in step 4, we reach our conclusion. Since we have proven that these two triangles are identical in shape and size, all of their corresponding parts must be equal. We call this CPCT, or corresponding parts of congruent triangles. Because of this, the length of side PQ must be exactly equal to the length of side PR. Now that we have set up our construction on the previous slide, let's dive into the actual proof. I'll show you the first method, which uses the concept of triangle congruence. As we will see in the next slide, there is actually a second way to arrive at this same result using the Pythagoras Theorem. Method 2, using the Pythagoras Theorem. Now, while the congruence method we just discussed is a very elegant geometric way to see the symmetry, I want to show you a second way to arrive at the same conclusion. This second method is more algebraic and relies on the properties of right-angled triangles that you are already familiar with, specifically the Pythagoras Theorem. Let's start with step 1. We will look at the first triangle we identified in our construction, triangle OQP. Since we know from our previous slide that the radius meets the tangent at a right angle, we can apply Pythagoras here. This gives us the equation OP squared equals OQ squared plus PQ squared. Now, since our goal is to find the length of the tangent, let's rearrange this formula to isolate PQ squared. By subtracting OQ squared from both sides, we get PQ squared equals OP squared minus OQ squared. Moving on to step 2, we apply the exact same logic to our second triangle, triangle ORP. Using the Pythagoras Theorem again, we have OP squared equals OR squared plus PR squared. Just like before, let's rearrange this to solve for the tangent length, which gives us PR squared equals OP squared minus OR squared. Finally, in step 3, we compare these two results. Remember, as we noted in our setup, OQ and OR are both radii of the same circle, so they are equal in length. If you look closely at our two new equations, you'll see that the right-hand side of both is identical. It's just OP squared minus the radius squared. Because the right sides are the same, the left sides must be equal as well, meaning PQ squared equals PR squared. To finish the proof, we simply take the square root of both sides, which leaves us with the final result, PQ equals PR. As you can see, whether we use triangle congruence or algebra, the conclusion remains the same. Now, let's see how this mathematical principle actually applies to a real-world scenario. Real-world example, the circular garden path. Now that we have mastered the formal mathematical proofs using both triangle congruence and the Pythagoras theorem, let's step away from the abstract diagrams and see how this theorem actually applies to a real-world scenario. Imagine you are standing at a specific spot, which we will call point P, in a large park. In front of you is a beautiful, large circular flower bed. You decide you want to walk from where you are standing to the very edge of this garden. However, you want to take two different paths, one heading towards the left and one towards the right, but there is a catch. You want your paths to be perfectly straight and just barely touch the edge of the circular garden without cutting through the flowers. In geometry, these paths are what we call tangents. Let's break this down step by step, using the logic we just learned. First, let's look at the setup. Your starting position is point P, and the center of this circular flower bed is point O. Next, consider your paths. You walk along a straight line to touch the edge of the garden at point Q on the left side, and then you walk along another straight line to touch the edge at point R on the right side. Now, here is where the geometry comes into play. Because these paths are tangents to the circle, the theorem we just proved tells us that the distance you walk to the left, which is the length of the segment PQ, must be exactly the same as the distance you walk to the right, which is the length of the segment PR. To put a number to it, if you were to take a measuring tape and find that the distance from your position to point Q is 10 meters, you don't even need to walk to the other side to know the truth. You can be absolutely certain, without any further measurement, that the distance from your position to point R is also exactly 10 meters. This practical application shows that the symmetry we discussed in our proofs isn't just a mathematical trick. It is a predictable property of the physical world. Now, before we wrap up, let's look at some common pitfalls where students often lose marks when applying this theorem. Common mistakes to avoid. First, let's talk about a mistake I often see when students use the Pythagoras Theorem, which we just looked at in Method 2. Many students mistakenly identify the tangent segment as the hypotenuse. Please remember that the hypotenuse is always the side directly opposite the right angle. In our specific construction, the line segment joining the center, O, to the external point, P, is the hypotenuse. If you misidentify this, your entire calculation for the length will be incorrect. Second, a word of caution regarding your geometric reasoning. Never assume that PQ equals PR simply because the lines look equal on your paper. In geometry, visual appearance is not a substitute for a logical argument. You must always explicitly state your reasoning, using either the congruence of triangles or the algebraic properties we've discussed to justify that equality. Finally, do not forget the fundamental property of the radius. The entire foundation of our proof, both the RHS congruence and the Pythagoras method, relies on the fact that the radius is perpendicular to the tangent at the point of contact. If you are writing out a formal proof and you forget to state that angle OQP equals 90 degrees, your proof will be considered incomplete. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even when you understand the logic of the theorem, it is very easy to make small errors in your written work or your calculations. Keep these points in mind as you practice, and you will find much more success in your geometry problems. Now, let's move to our final slide to summarize everything we have learned today. Key takeaways. First, let's restate the core theorem. Remember, any tangents drawn from a single external point to a circle are always equal in length. This is the fundamental rule we've been working toward. To visualize this, think back to our geometric setup. When we connect that external point to the center of the circle and to both points of contact, we aren't just drawing random lines, we are actually creating two congruent right-angled triangles. This symmetry is what makes the theorem work. As for the proof basis, we have seen two distinct ways to prove this equality. We use the RHS Congruence Criterion, which stands for right angle, hypotenuse, side, and we also use the Pythagoras Theorem to show the algebraic equality of the sides. Both methods lead us to the same undeniable conclusion. Finally, never forget the essential property that serves as the foundation for this entire lesson. The radius of a circle is always perpendicular to the tangent at the point of contact. Without that 90-degree angle, our triangles wouldn't be right-angled, and our proof would fall apart. All right, we have reached the end of our lesson. Let's take a moment to recap everything we have covered today so you can consolidate your understanding. Keep these points in mind as you practice your geometry problems. Great job today.